This property of matrix arithmetic tells us that if we have to multiply a certain scalar to already a result of another scalar beta with a matrix A, we can just simply try to use here the associativity of scalars and multiply it to the same matrix, and the result would be the same. So as you can see here, this is on the scalar associativity with one of the matrix A. So it's just, they are just of the same value. To do this, of course, we are going to let A be describe, or we're going to describe a certain expression that will be equivalent to our matrix A. And since we are dealing with all types of matrices, so we are not going to use a 2 by 2 or 2 by 3, but we are going to use here an m by n matrix. So in general, it has n number of columns and m number of rows. So for that, we can express our A in this manner. You have A11, A12, A13 until your nth column. And for the rows, you will have A21, A31 until your mth row. You would say this is correct because you could have here a final component which corresponds to mn. If we're going to continue, A22, A23, A2n. Okay? I would like to caution you that if you're going to prove matrix arithmetic or involve any proof involving matrices, you really are going to have a lot of need a lot of patience in proving that, because it will take a lot of time. As you can see, we're doing here this dot 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 because it is, we don't know the exact value of m and n. So you have here am2, am3 until amn. Okay, and of course we're going to let alpha and beta be scalars, or they could take any value of a number. What's our goal here is, from here, you would like to manipulate this left-hand side and arrive to our right-hand side using these expressions. So if we have here the product of alpha and beta A, okay, so before we start, let's try to come up with an expression of how does matrix beta A looks like. So this means we're simply multiplying the scalar beta rather to our matrix A. That would mean we are multiplying again beta to all the components of our A, A11, A12, A13, A1n, A21, A22, A23, A2n, A31, A32, A33, pardon my handwriting, A3n, until your mth row, AM1, AM2, AM3, and AMN. So how do we show the result of this? When you have a scalar, multiply that to all the components. Hence, beta A is equivalent to this expression: beta A11, beta A12, beta A13, dot dot dot, beta A1n, beta A21, beta A22, beta A23, dot dot dot, beta A2n, beta A31, beta A32, beta A33, dot dot dot, beta A3n. And here, so let's try to extend it here: beta AM1, beta AM2, beta AM3, dot dot dot, beta AMN. So this is the expression equivalent to our beta A, which is A, the matrix A now. So let's try to use that here. So you will have alpha times this result. Okay? So you have beta A11, beta A12, beta A13, dot dot dot, beta A1n, beta A21, beta A22, beta A23, beta A2n, that's n, beta A31, beta A32, beta A33, beta A3n, and you will have beta AM1, that's until here, beta AM2, beta AM3, dot dot dot, beta AMN. Okay, so similar to what happened earlier where we multiply the scalar to all the components here, just like that, we're also going to multiply alpha to all the components here. So you can have this next form. Again, our goal is to reach this form, so we are getting closer to that. You have alpha times beta A11, alpha times beta A12, alpha times beta A13, dot dot dot, alpha times beta A1n. Okay, so you have alpha times beta A12, sorry, it's now 2 1, it's the second row, alpha times beta A22, alpha times beta A23, dot dot dot, alpha times beta A2n, alpha times beta A31, alpha times beta A32, alpha times beta A33, dot dot dot, alpha times beta A3n, until your mth row. Alpha times beta AM1, alpha times beta AM2, alpha times beta AM3, dot dot dot, alpha times beta AMN. Okay, so hopefully you've been following. This was actually what was used here, so they are not of the same level. This is actually the first steps, and then this one here. Now that we have this, since they are now under each component, and they are, if this A11 is another real number, we can just simply use here the associative property per component. Hence, you will have this form. Okay, associative property per component. You can group the scalar alpha beta A11, alpha beta A12, alpha beta A13, dot dot dot, alpha beta A1n. Okay, alpha beta A21, alpha beta A22. It's also important for us to remember our end goal here so that we could actually think of what will happen on our proof. Alpha beta, that's why we are grouping now alpha and beta. A23, dot dot dot, alpha beta A2n, alpha beta A31, that's 3, alpha beta A32, alpha beta A33, alpha beta A3n. That, and then to the mth row. Sorry for that again, I was not able to really estimate it properly. Alpha beta AM1, alpha beta AM2, alpha beta AM3, alpha beta AMN. Now that we are done with this, we cannot, since alpha and beta are both scalars, their result or their product is also a scalar. Now we can move that out because it's on each of our component. So we could have this expression, alpha beta times, what remains, it would be these components, A11, A12, A13, A1n, A21, A22, A23, A2n, A31, A32, A33, A3n. That here, AM1, AM2, AM3, and you have AMN. Of course, this is already okay because it's a product of the scalars, but to just really pattern with what we want to show, we could actually make this like that. And this matrix is already identified earlier as what we described as matrix A. So the next step would be the final step here. We can just simply have it like this. Alpha beta times this matrix, which is just matrix A. So as you can see, going back, this was our starting point earlier using the description or definition we had for A, and then this product of beta A. we implemented here. Our goal is to reach this, and that is actually the end result of our proof here. This is now the last part, or this is now the last part, or the end of our proof. And as we have shown that these properties of matrix, where we have two scalars, but one of which is already multiplied to the matrix A, we just simply just take the product of the scalars first before multiplying it to A, and we'll have the same result. This is properties, laws, and theorems. Please subscribe now.